Hello everyone. With this example, we're going to see if we can associate some engineering structural calculations as they relate to soil and how they can affect building construction, the sizes of footings, foundations, that sort of stuff. With this first one, we're going to try this. We have some kind of a pier that's coming down onto a pad footing. Okay? We don't know the details yet, but we know that from the building above or whatever structure above, the loads that are being funneled all the way down onto this pad footing are 84 kilonewtons. At the moment, we don't care how we came up with this number, it's given to us. We also have a pad footing. I'm going to let you know that we've decided that the dimensions of this pad footing is 800 millimeters by 800 millimeters. Okay? Just like that. 800 millimeters square, 800 millimeters on side. This pad footing is sitting on loose sand. And as you found in the lecture, for the purposes of our course, we're going to use the bearing capacities we find in part 9 under table 9.4.4.1. So for loose sand, it's 50 kPa. That's 50 kilopascals. The question is this acceptable? Is the size of this pad footing acceptable given what's been given to you? So let's find out. First of all, we have to decide whether or not we understand this system, this setup of this example. So I've tried to sketch it on this side, just including the forces that are at play. We have the building forces, right? These gravity loads that are coming down from the structure above. And they're coming down by a magnitude of 84 kilonewtons, right? Remember, kilonewtons is a unit of force, a load. And then we have the resistance of the soil under this pad footing that's been given to us as 50 kPa. We found this because we're told it's loose sand, and we went to this table to find it. The resistance of the soil, the bearing capacity of the soil, it's in kPa. Kilopascals, and that's a unit of pressure, okay? And from an engineering point of view, this is a force per unit area. So what that means is this is a better representation of what the soil is doing under this pad footing, right? So per unit area, it's resisting 50 kPa. Now I want to remind you, I know you know this, but I just want to remind you, 1 kilopascal is equal to 1 kilonewton per meter squared. Okay? So that's how it is a unit of force over an area. That's the bearing resistance of the soil. How much the soil can resist. So basically, we have to try to figure out if the amount that the soil is pushing back up under this pad is sufficient to hold up the applied force that's coming down from the building. Let's find out. Let's compare them right away. Well, we cannot quite compare them because this is a force and this isn't a force. This is a force per unit area. We're not comparing the same thing. The only way that we can compare these two is if we either converted this to a force per unit area or converted this to a force, right? We have to compare the same thing. We have to compare force with force or force per unit area with force per unit area. So here's what I propose, okay? This here, being a force per unit area, is something, an amount of pushback that is under a specific area given to us already, okay? So if we could somehow work this out to figure out how much single point force is under this pad footing, then we can compare that single point force against this, whether it's bigger or smaller. So let's try to use this analogy, okay? Some of us like, say, something like toast and peanut butter for breakfast, or some other spreadable substance on bread, or some other flat surface, okay? Let's use peanut butter just to pick something, or even just Nutella, okay? So from the jar of Nutella, when we take out our knife, we scoop out a big glob of peanut butter. That single glob, right, is all in one spot, right? That's a force. However, when I put it on toast and I spread it, suddenly that becomes a force per unit area because you've spread it evenly over an area. So I propose that I show you how to take this peanut butter that's been spread under this footing, right, on the underside of our toast, if you will, and put it back together into one single glob so that it becomes one force we can compare against the applied one. And that's where engineering comes into play, right? We have to remember that bearing capacity, right, the bearing capacity of soil is simply this. Bearing resistance, okay, is equal to a force divided by an area. Right? That's why I call this pressure at the beginning of this video, because that's really all it is, right? Even in engineering terms. Now, here's the thing. We have this value. We can find this value, right? It's the area of the underside of that pad footing. What we want to find is force. So if we manipulate this, and I know you know how to do it, but I won't test you on it, I promise. What we get is that force equals to bearing resistance times area. Okay? So here's what we're going to do. We're going to put in here the bearing resistance, and we're going to put in here the value of the area. So let's see if I can figure out what the area is. I have a bit of room here. I'll write it up there. Area is 800 millimeters times 800 millimeters. Okay? 2 out of 3 times when I did this, I got this answer. 640,000 millimeters squared. Now this is not proper engineering notation, but I'm just doing this so I keep track of all the zeros. So can I put in here then, as I'm figuring this out, force equals to, bearing resistance is 50 kPa times, look at this, 640,000 millimeters squared. 640,000 millimeter squared. Well, the concept makes sense. I put in the quantities as I have them, but I can't just multiply them by each other. The units don't work out. I want to get a force in kilonewtons, right? And here I have kilopascals, and here I have millimeters squared. Wait. Kilopascals is also kilonewtons per meter squared, right? That's the definition of bearing, of pressure. So if 1 kilopascal is 1 kilonewton per meter squared, 50 kilopascals is 50 kilonewtons per meter squared. That helps, okay? So this is equal to 50 kilonewtons per meter squared times. So that's great. Look at this, okay? Now we have a force as a unit and an area as a unit. Now, this here, 640,000 millimeters squared, if we could convert that to meters squared, that would work out. So how do we do that? How do I go from millimeters squared to meters squared? I know you know this, so I'll tell you right away. You would have to divide by 1 million, right? 1 million meters squared per millimeter squared, right? To convert it. So what we get here is that 640,000 millimeters squared is equal to 0.64 meters squared. Right? So I converted this now to meters squared, which is great. Look at this. Meter squared and meter squared cancels out, and we're left with only kilonewtons, which is the right unit for a force. So I'm going to use red to indicate a force. 50 kilonewtons per meter squared times 0.64 meters squared gives us, that's 2 out of 3. I get 32 kilonewtons per kilonewtons. And I'm saying best 2 out of 3 because I mean it, right? When you're doing calculations like this, it's good practice to check your answers. Especially once you start trading time for your money, right? Once you become a professional, and the results of your calculations may affect the building you're designing, right? You don't want to kill anybody by under-designing something. So it's always great to check your answers. So what I get is that the force here under the footing is 32 kilonewtons. Is that enough to resist the applied force coming down from the building of 84 kilonewtons? That's no good, right? This here is less than 84 kilonewtons. Right? So therefore, not acceptable. Right? What we have here is no good. So then, we can stop here. Or you can keep watching, because then I'll discuss a little bit what could we do to fix this. This is extra. Okay? So if you're still here, here's what we could do about this. Well, there are a few variables that we have control over, right? In an ideal world, we could change the dimensions of this pad footing. Does that make sense? If we made the area bigger, well then this might work, right? It's the same thought process that comes that is behind, say, using snowshoes. When you're walking on snow, you want to make sure that your snowshoes are wide enough to distribute your weight over snow so you don't sink in it, right? So that's one thing we could do. We could increase the area, right? Another thing that we could do maybe is change the kind of soil we have under here, because that may increase the bearing capacity of that soil, right? Make this larger. Another possibility is that we could reduce this value, the amount of load coming down from the building, right? Ideally. Now, if this, say, is an existing building, this is very hard to do, because it would require, say, changing tributary areas, widths, that sort of thing, of a structure that's above. That's really expensive, okay, and a real headache. Changing the soil under your footings, well, it's possible, but it can be expensive, right? Especially depending on the size of the building, what the occupancy is of that building, the access you have, because you have to go under the building to basically replace the soil, while holding up the whole building. Doable, but expensive. Increasing the size of this footing is likely a better solution, because from a cost point of view, it's the lower option, but it just has to be done correctly. You cannot, say, just put a form outside of this and pour more concrete to make this bigger. That's not how it works. You have to properly attach new concrete under this to increase the size of that footing. It has to be done properly. Okay, but those are the three things that could be done. Increase the size of the pad footing, put better soil under here that gives us more bearing resistance, or somehow reduce the amount of force coming down on the building. Make sense? Lovely. I want to thank you so much for your time. There's going to be links at the bottom of the video to the original lecture, and I hope to link also the other examples that I've covered for you. Take care and have a lovely day.